Welcome to the PSYC 2700 Quantitative Methods in Psych Lab narrated slideshow. Basically, we're at the end of the semester and we've learned a lot of statistical analysis, some statistical significance tests, and basically I wanted to show you that if you're not crunching the numbers by hand with formulas, you can also use statistical analysis software to come to the same conclusions, to do the same significance test. So that's the point of doing this lab, is to get away from using the formulas with our hands, but also seeing those formulas at work in some of the output we get. So that's the whole point and my goal of doing this. And basically this is part of any Psych 2700 class in the BGSU system. There should be a lab component. You should actually see statistical analysis software in play. So again, that's what we're going to do here, and you'll have plenty of resources available to you as well when you complete the lab. Basically, it's asking very specific kind of questions that should be familiar to us, but here's where we're at the end of the semester, and we can think about how is this test different from that test? How is a one sample t-test different from a repeated measures t-test? And how is that different from an independent samples t-test? So hopefully it'll serve as a review function as well. Also consider you have the resource of your textbook. So at the end of every chapter, or sometimes more toward the middle of the chapter, the textbook does show statistical analysis output. They show the numbers, they show the statistical test to help us determine significance and make conclusions about our data. So we're going to be doing those same things in this lab. So if you do have questions about some of the output we're looking at, it might be helpful to use your textbook as a resource and look at the output there. Because we're essentially doing the same thing and looking at the same numbers, even though the actual tables may look slightly, although not very different. So for example, what we have here is a data set, and you can see this is just a screenshot of the Excel file that you can view to complete the lab if that's helpful. And I think it is important to look at the raw data, and so we see each row is a different person, and for each person we have measures on 1 to 10 variables. And you can see, and also we'll get to the explanation of this data, anything that has a decimal in it, that's going to be a continuous variable. Also these, we're going to find out a quiz score, a quiz early in the semester, midway through the semester, later in the semester. Is there an improvement anywhere along the semester on this quiz? And then we have final exam score in terms of a percent. And then we have the actual percentage in the class. So what we're seeing here is nice continuous variables, and also we have these 1s and 2s. Now they could be continuous variables, and so 1, 2, 3, 4, but usually these represent codes. And if we think about what are these variables, what do they look like in a survey, for example? They're not gender on a scale of 1 to 10, it's gender, just check this box or that box. So they're not continuous. In fact, they're discrete. So this would be a categorical variable of gender, and you have the actual code in your lab with the questions sheet. But if you ever need to go back and look at the raw data, you have this sheet available to you, the Excel file, and you can see male. I'm guessing Alfred's a male, Scott's a male, he's coded 2. Jackie and sound like females, they're coded 1. So if you're a female, you get coded a 1, male coded a 2. Similar thing for year, except instead of having 2 categories, we have 4 categories. So seniors are 4, freshmen are 1, and sophomores and juniors are 2s and 3s. We also have extra credit, no versus yes. Did you intend an extra credit or do an extra credit option? Again, 1 should be no, 2 yes. And then a review session. Maybe there's an optional review, either 1 no, 2 yes. So it's important to, and those codes are in, again, the sheet with the questions in the lab to tell you exactly what a 1 or a 2 means for extra credit versus review. But again, this is exactly what the data looks like in terms of the raw data in the spreadsheet. Now the next thing we want to do is think about all the questions we could ask about this. So for example, is gender, your gender status, is that related to your GPA? That sounds like a t-test to me. Or, for example, is your year in school? We have 1, 2, 3, 4 categories. Is that related to your GPA? Well, now we have more than 2 categories, so we can't use a t-test, so that sounds like an analysis of variance to me. More than GPA for freshmen, GPA for sophomore, GPA for juniors, GPA for seniors. That's 4 means we're going to test significant differences with, so we have to do analysis of variance. We also have, for example, with any of this categorical data, we can test how many people did go to the extra credit and how many people didn't do the extra credit, how many people did go to the review, how many people didn't, and does that match a prediction that we predicted 75% of people would go and we found out actually only 50% people went. So would that be a significant difference between our prediction and the actual values? We're thinking in terms of only this continuous variable, so we're in chi-square territory. Or is attending the extra credit event related to attending to the review event? Is there a relationship between these 2 categorical variables? And that could be a clear chi-square type of question. Again, chi-square test for independence. Or is it not independent and these variables are actually related? So just an example of how looking at this data, given all the statistical analyses and significance tests that we've already learned, there's a whole bunch of questions that we can apply to this. And so it's important to know what kind of variables do our hypotheses involve, and that's going to lead us to the analysis that we need to use. So that's a big part of this lab, is seeing, given this kind of data and a number of the questions we could ask, what statistical analyses and significance tests would be appropriate to answer our question. So here we see basically the question sheet. So what I want you to do is have word processing software and then start writing your answers to the questions that are below in the PDF, if you look for that in Canvas in the lab materials module. What I'm looking for is a blend of both the numbers, so which 2 means are being compared, and is there a difference? Is there a significant difference? How do we know there's a significant difference? That's usually when we're involved with a statistic. You know, is our F ratio significant? Is our T statistic significant? And we'll see that the output's really going to help us to answer those questions. So what I'm looking for is in your write-up, the combination of explaining, interpreting what the statistical test tells us about the variables, and also reporting the results of that test. Report with the degrees of freedom, using the right notation, what does the T statistic tell us, and then explain what that means. Also, as mentioned before, when we think about our data, we have the codes for, again, if they attended the review or not. 1 is a no, 2 is a yes, and whether they did extra credit, 1 is a no, 2 is a yes. And then our 6 continuous variables, our GPA, final exam score, final class percentage, and these 3 class quizzes that took place over the course of the semester. So once again, thinking about this is what our data looks like in the statistical, or this is in our spreadsheet. So this is classic Microsoft Excel. And again, it's organized by rows and by columns. What we have here is essentially the same thing, except now we have an extra window. So this is opening up a data set, oftentimes just importing it from Excel into, in this case, Minitab is the statistical analysis software that I'll be using today. SPSS is the big one in the social sciences, especially for psychology. This is a more basic version, but you can see it has a number of drop downs. Oftentimes we're going to go to the statistics that we're looking for. We can also do basic calculations or data transformations. So if we need to square, for example, a certain column, we can make a new column and calculate the squared values of that column. Or oftentimes we can, for example, if we have the mean and standard deviation for a set of scores, then we can calculate using our z-score formula a new column that gives us the z-score for each of our individual raw score values. Also, there's a number of graphs that we could use. I'm not going to go over those today, but things from the beginning of the semester, such as stem and leaf plots, histograms, and bar graphs are all things that you can calculate here, but mostly we're going to be using the stat. And once we do our first stat, we're going to see where the results or the output come up in the output window. So now I'm just going to work in order of the lab from the very first one, a one sample T, as you can see. And basically we have our sample mean, and we're going to compare that to a known population mean that's given to us in the question sheet for the lab. And notice the progression. We go to statistics, in this case basic statistics, down to a one sample T, meaning we have a known population mean that we can compare our sample mean to, but we don't have the population variability or standard deviation, so we need to use our t-test. We can't use a z because we need both the population mean and standard deviation. When we only have the population mean, we have to use our t-test. So once we've clicked that, here's what we do. We're seeing if our mean GPA for our sample is significantly different from the population mean that we're given, 2.98. So very simple test, and all I had to do was double click GPA and then throw it in this box. That's the continuous variable that we have a mean for our sample, that we're comparing it to this population mean. And in the output, here's what we see. We see our sample size, we see our mean GPA, we see our standard deviation of that GPA, and then we even see the standard error. Also, we have a confidence interval around that sample mean. We haven't gone much into detail, but if you go into more advanced statistics, you may see the importance of confidence intervals. One thing especially, we know our population mean that we're testing it against. We're given our null and alternative hypotheses right here. And we see even our test population mean is higher than our confidence interval. That often means that, oh, there might be a significant difference. That difference is pretty big. And what we see is our t value, our t statistic, and then it's negative, showing that our sample mean is lower than our population mean. And we see a p-value of less than 0.05. So hopefully by now we know what to conclude when we see this to determine whether there's a significant difference between our sample mean and our population mean or not. Now we're going to ask a slightly different question. Now we're going to use one of the grouping variables or one of the categorical variables in our sample and say, well, we have two groups, mean for one group, mean for another group on a continuous variable. Do those means differ? So in this case, we're talking about two groups. You can only be in one or the other in our sample, oftentimes male or female. So that means we're looking for an independent samples T. And know that it doesn't say independent samples here, but we know that the paired samples, that's what we're going to use in a little bit for our repeated measures. So the one that's not paired is the independent samples t-test. Here's what we do in terms of adding our variables. So our ID is our categorical variable. So we popped in, double-clicked gender to go here. And we're seeing if the final exam mean for males is significantly different from the final exam mean for females. Is there a gender difference? Significant gender difference. And again, this is the independent samples t-test because you can't be, it's not repeated measures, you can only be either one gender, and is the gender average of your group different from the gender average of the other gender. And here we see the output. So clearly we see for gender, if we go back to our coding, what does a 1 mean? I believe 1 represented females, so we have more females than males in our group. And we do see that females have a slightly higher mean on the final exam than males. That's not very big, but is it significantly different? And we see our T statistic, and we see our P value for that statistic. One thing that seems off is our degrees of freedom. I don't know why that is showing it. That looks wrong to me. Maybe there's a reason for this, because it should be 2 groups, n of 105 minus 2. So I'd expect that degrees of freedom to be 103, but it's not hugely important. This is the T value that we're going to go with. Is it significant or not, given that we have a P value that is way over 0.05. Moving on, now we are looking at a repeated measures question. So has there been change over time from time 1 to time 2? So this is where we select the paired T test. Again, the same items, but at different times. So basically, our paired T, I don't know why it calls sample 1, sample 2. It should probably call it time 1 and time 2, but maybe somewhat confusing label aside, what this is doing is taking quiz 1, and our whole sample of 105 people have a value for quiz 1. Is that mean for quiz 1 significantly different, or has changed significantly to quiz 3? Again, the quiz has the same questions at time 1, time 2, and 3. Is there a significant change over time or not? And here we see the output. So again, 105 people took quiz 1, 105 people took quiz 3, and we see that the mean, there is a mean difference, but is it significant? So again, we see our hypotheses laid out for us. We see our T value looks pretty big, and our P value is definitely less than 0.05, a less than 0.05 chance that we make a type 1 error if we reject the null hypothesis. So again, you should know whether that is a significant outcome, a significant difference or not. Now we are moving on to looking at comparing more than 2 means. And when we have more than 2 means, we have to leave the t-test territory. So in this case, we can select analysis of variance or ANOVA. We could also do one way for this, but general linear model is another way. This basically, one way just means testing variables on one factor or one independent variable, or categorical grouping variable. General linear model lets you do a whole lot of other stuff, but also the basic analysis that the one way does. So either one would be okay to use. And here's how we plug in what we want it to do. We're telling the statistical analysis software Minitab what we want to do. And we're essentially saying year in school is the factor. And year represents freshman, sophomore, junior, senior. They're each coded with a different number, 1 through 4. And of course, that is a between subjects factor, because you can't be both a junior and a sophomore. You have to be one or the other. And then the continuous variable that we're testing if there's mean differences by year on is GPA. Also, we want to consider if there's an overall significant finding for our F ratio, and we're comparing 4 different means, the means of 4 different class years. Well, the F ratio won't tell us where the significant difference in the means is. So that's why we want to do a post hoc test. And so we've selected the comparisons button, brings us to our post hoc options, and specifically we wanted to choose the Tukey test. Now this is both the output for what we're doing now, the between subject ANOVA, and then this is also for the repeated measures ANOVA. So we're going to ignore this one for now. We're going to look at the between subject ANOVA. It gives us our hypotheses, gives us our significance level that the F ratio is tested at, and it gives us a bunch of numbers that might seem kind of difficult to understand at first, but let's try and break this down. It's showing our year of factors has our 4 coded values that we saw in the raw data. Looks like that's working okay. We also see our different sources, our total variance versus our error variance versus our grouping or between subjects variance, and we have 4 groups, so degrees of freedom, 4 groups minus 1 gives us a degrees of freedom of 3. That makes sense. And we see our F value looking pretty low, and our p-value is very far from being less than 0.05. Now we can largely ignore some of this stuff here, but it does give us our n sizes. What's wrong with only having 3 freshmen? I don't know. That's what the data says. And we look at the actual means of GPA for freshmen, sophomore, junior, senior. They're not exactly the same, but they're pretty close to the same. What the Tukey does now, if we say there's a significant difference here, and you'll have to interpret whether you think there is or not, this grouping variable or category will tell us which groups are significantly different. So any group or year in school that has a different letter than the others means it's significantly different from the others. So that will also help you in deciding whether there's any significant differences here. Now we're going to move on and do a repeated measures or a within subjects analysis of variance. So that means we have at least 3 or more different times that we want to see if there's change. And again, we can still go to the general linear model. One thing to keep in mind is I won't show the actual dialog box of entering the variables because there is some stuff that I had to do with the data in the data set, and then I did have to do some maybe a little bit confusing for our purposes stuff in the dialog box to make sure it was running the analysis I want. So one thing to remember then is that if you're doing a repeated measures analysis of variance, that's when things can get difficult. And then of course, we remember from the book and the narrated slideshow that ANOVA is very flexible for doing much more complicated analyses, multiple factors, multiple predictors, for example, or independent variables, and the interactions between those predictor or independent variables. So this is where things start to get complicated, and where especially for our purposes we start to drop away from the math because it gets hard to do by hand, and it also gets more difficult to point, click, and shoot, but it can be done. So again, on the left is what we've just been over, our between subjects ANOVA. Now on the right we have our repeated measures ANOVA. And so what we're looking for is that quiz that we know they took 3 times, and is there, and we can see there are 3 levels of time. And so now we have, first of all, our sources of variability, total variability, error, and here's our between or repeated measures factor. And notice 3 times minus 1 gives us a degree of freedom of 2 for our time. And now we have this person. That is our between subjects source of variability. And remember, we identify that and can pull it out when we have a repeated measures design. And it's saying there was significant repeated measures, or between subjects, excuse me, between subjects variability. That's not exactly what we're interpreting here. What we really want to interpret is this factor here. Is there significant difference between the times? And we see a big F value, definitely below an alpha 0.05. So yes, there's a difference here between one of the 3 times, at least one of the 3 times. And then we have our Tukey post hoc test. And this is showing us 3 means for quiz 1, 2, and 3. And where is the significant difference? And you should be able to, from this grouping method, see that there's a significant difference here somewhere, and now our post hoc test tells us where it is. Now, moving on, not much to say here. Correlations, as we've talked about, once you've got them measured in a way you trust and into the spreadsheet, it's so easy to point, click, and shoot and do correlation. So if we have just simple bivariate or 2 variable correlation, GPA and class percent, we see the correlation and we see whether it's significant or not. Now what's really helpful though is correlations are kind of a weird thing because we think of them as doing a significance test, but they're also kind of a way to look at descriptive data. So oftentimes you'll see descriptive data such as for each of these continuous variables, GPA, quiz scores on 1, 2, 3, and class percent. We have a mean and a standard deviation for each of them. And oftentimes in a correlation table, providing the descriptives, you'll have on the left side, this is in published research, you'll have all the variables, the means and standard deviations, and then you'll have this part folded in here in the same table. Oftentimes you'll see asterisks marking significance rather than the actual p-value. We don't need to know the actual p-value just to know whether it is below 0.05 significant or above 0.05 not significant. And you can see these cell contents clearly label. The top one is the correlation. So we have a positive correlation here between quiz 1 and GPA. The better you did on quiz 1, the higher the GPA you have. But then we look at individually, which is the highest correlation of these variables with GPA, we see that percent has the highest correlation. So percent is the best predictor of these others, of the quiz scores of GPA. And notice we see a lot of significant values in here, lots to interpret in terms of thinking about what's related to what with these correlations in your write-up. Now we're doing a regression, and kind of like working through correlation, two variables you can do a regression for, and it's pretty simple. But what we're going to really enjoy is being able to do multiple regression and seeing multiple continuous variables predicting one continuous outcome variable. But here we just have one. So for example, we look at this, all of this numbers, we have our significance test here. The cool thing is that we have our regression equation. So what we're seeing here is that we are predicting percent in the course, and we have our y-intercept here. So everybody, when we're predicting people's grades, we start at 60%. Everybody is going to, in our sample, at least got a 60%. Now, if somebody ended up with a percent below 60, that's in a new sample, then our regression equation may be a little less trustworthy. But for this sample, 60 was, we're starting with 60, and then for every GPA unit, our one predictor, we add 6.99 points. So that's our regression equation, and we want to see, is it significant? Is GPA a significant predictor of percent? And we can see the F value, that's pretty big, and we look at the P value, is that significant or not? Notice the regression and the GPA are the exact same numbers. Why? Well, because the regression is looking at the set of predictors all together, and since there is only one predictor, that one predictor is doing all the work for the regression in significantly predicting the outcome. Now, once we get to multiple regression in the next slide, we'll see how that can be a little bit different moving forward. So now we see multiple regression, and from our regression equation again, we see we are predicting class percent, but now we are using GPA, quiz 1, quiz 2, and quiz 3. So now if we're predicting percent, we're just starting everybody off at 30 and then adding 3.3 units for each GPA unit, 1.3 for each quiz 1 unit, and so on and so forth. And we see overall this set of predictors, this tells us whether that is significantly predicting our outcome of percent. That's what this row up here is doing. Then we know that if there's significant prediction here, at least one of these variables has to also, one or more has to also be predicting, because these can't be individually not predicting. but as a set predicting. There are some exceptions to that, but for our purposes, let's consider that. And we see the F value for each of our individual predictors and whether that is significant predicting or not. And then we see, add them all together, what is the combined F and the significance. And you can also see, interestingly here, the R squared, which is the percentage of the percent outcome variable that we are predicting that this set of predictors accounts for. And our set of predictors accounts for 80%, over 80% of our outcome variable of class percentage. So that means we got a good set of predictor variables. We can account for almost all the variability or explain or come pretty close to 100% prediction with this set of predictor variables in multiple regression. Now we're going to wrap up with where we ended up in terms of our class content, and we're talking about chi-square. And first of all, we have the chi-square goodness of fit test. So we're just looking at a categorical variable, one categorical variable, and does it match our test proportions? So in the lab question sheet, it's asking if we were testing our observed counts for gender, and again, 1 is female, 2 is male. We have to look at our coding to double check that, or the raw data. But we see we have more females than males, and we expected, based on the numbers and I don't have the dialog boxes because I had to finish this narrated slideshow at home in Minitab, and the license, for example, for Minitab doesn't work for me, so I can't bring up the dialog boxes, but it's chi-square goodness of fit test, point, click, and shoot in Minitab to bring up ultimately this output. So again, this is our expected ratio of 105 divided by 2. Of course, you can't have half a person, but that's what we're testing the math in. And we see our observed is not a 50-50 split of females and males. And we see our chi-square looking fairly robust, not humongous. And then we see, is our p-value less than 0.05 and significant or not? So does our observed counts, are they significantly different from a 50-50 split? And this is where our answer lies. And then finally, still on chi-square land, still working with discrete or categorical variables, here we see, for example, gender again, and our other categorical variable is, did they do the extra credit, yes or no? So 1 should be no, 2 should be yes. Is there a relationship between one gender doing more or less of the extra credit than the other gender? And here we see our frequency table, and here we see our counts. So we see 53 females did not do the extra credit, 30 males did not do the extra credit, 11 females did do the extra credit, and 11 males did do the extra credit. So we can see there's a greater ratio. 1 out of 4 males did the extra credit, whereas 1 out of 6 females did the extra credit. And notice what we see here is a Pearson kind of correlation, 2 different tests. It's basically taking these categorical variables and pretending if they were continuous in terms of a correlation, is there a significant relationship here? And we see our chi-square value not super high, and then we see the p-value associated with that pretty far away from 0.01 and definitely not lower than p of 0.05, pardon me. And so that will determine our conclusion about whether these 2 categorical variables are related or not. So again, what are these values in our table? These are our observed values. And then if we applied that formula, we have to test them against our expected values. But that formula, of course, can give us decimals. So these are just the expected values in the cells related to the actual values we got. And we see there's not huge differences between the observed and the expected over and over again. So like there are some differences, but are they significantly different? Well, our chi-square test tells us whether or not. So hopefully that helps you as you work through the lab. And of course, let me know if you do have questions or difficulties along the way. And hope this will be useful for you and hopefully give you some confidence that you can actually collect data. And if you have data, then you can do these analyses yourself. A lot of the statistical software is available on the machines, especially Minitab, at BGSU and at BGSU Firelands. So don't be afraid to play around with statistical software and hopefully move forward in your journey in statistics and psychology.